Hey everybody, and welcome to another simple science video. And in this video we are going to be looking at elastic potential energy. So following up from our previous video on Hooke's law, we are going to be looking at an energy that is very important in our strain system. Alright, so when an object is strained, in other words, when we allow tension to act inside its body, in other words, we can stretch or compress this body, we must do work. And when we do this, we must apply a force in order to cause it to undergo tension. And this force, when it acts through a distance, distance is usually the extension or the compression distance, and that distance accounts to work when we're considering the force that acts through that distance. All right, so we are doing work to cause this object to be strained, and this energy doesn't just go anywhere when we stop basically moving this force. This work is transformed into potential energy inside the object. Alright, so we basically give the object energy. And this potential energy is called elastic potential energy, which pertains to the system that we're basically dealing with. So we know that F is equal to kx, where x, the extension, is directly proportional to the force, and we know that the force in which we apply will correspond to the tension that is within the string. Alright, and since work done is equal to force times distance, and F and T are numerically equal, then work done is equal to T times D. Alright, so the work done we need in order to cause this thing to undergo tension. So to reiterate, F is equal to Kx, T is equal to Kx, work done is equal to Fd, and work done is also equal to Tx. Okay. Alright, so we know that work done is equal to Tx, but in order to find the energy in which the object has at a particular amount of extension, we are not going to be dealing it with in a linear sense, because the tension within the object actually varies with the extension. It makes a lot of sense, because the further we try to basically pull the spring out, the stronger the force in which it's going to pull back on us, basically. Alright, so work done, unlike the force, does not vary linearly with the extension. Okay? And the work done, as we know, when we're looking at integration, as a result, as it's not linear, we have to use integration, is equal to the integral of the tension force, which varies with the extension, with respect to x. Alright, and the limits that we are going to integrate this through is through 0, when there's no extension, and our final extension, which is e. Alright, I'm basically replacing x with e. And let's do a basic integration. We know that work done is equal to integral of t with respect to x. And since t is equal to kx and k is basically a constant, we further integrate this function. We get square brackets kx squared over 2 with the limits of o and e. And when we solve this integral, we get k squared over 2 is equal to the work done. Alright, and that is basically the elastic potential energy at a particular extension. Okay, and this will make more sense when we're looking at our situation from our graph. So we know that work done is equal to Tx, basically the tension multiplied by the extension. And since T varies, obviously, you can see the T, the force, which is equal to F, it varies, alright? And the force in which we are going to point out is Ke, which is the spring constant multiplied by the extension, and that corresponds to an extension of E, alright? And since the work done, we know, is the area under the graph, because force times extension will give us the area, and the force varies, so this would make sense that an area under the graph would be the elastic potential energy. In other words, the work done that we must apply in order to cause it to be in tension at that extension. Alright, so the work done under the graph, in this case, for our corresponding values, is E multiplied by Ke over 2, basically the area of that triangle. And therefore the work done is basically Ke squared over 2, and that basically is your elastic potential energy. And to summarize it quickly, when an object is strained, there is elastic potential energy, and through integration or basic understanding of the Hooke's law's graph, we get that work done is equal to K squared over 2. Thank you for watching my video. I hope you enjoyed this video and found it very informative, and basically have a nice day. Check out my previous videos on work, energy, and power to make sure that you haven't missed anything out.